This talk was given at the August 2013 Mars Society Conference in Boulder, Colorado, on the subject of radiation and space travel. It is based on the book Radiation Exposure and Its Treatment by Brian Hanley. And here is Dr. Hanley.
First thing I want to talk about, because cancer is the major issue with radiation, is what causes cancer. A lot of things cause cancer. Viruses cause cancer. For example, we currently have the HPV vaccine. It's a little controversial, but it protects against certain types of cancers. Inflammation over long periods from virtually any source is associated with cancer development. There's far too many chemicals to list. Everybody knows about the coal tars in tobacco. Diet. Vitamin D is protective. If your vitamin D levels are low, your chances go up, although vitamin D does not work as a treatment. The switch to sea salt has brought the average dose of iodine down by about 50% from what it was in 1950. And this is a likely cause of, or one of the likely causes of the breast cancer epidemic. If all you do is, if you're a woman, is don't use sea salt, use iodized salt always, will probably be a significant thing you can do to avoid cancer. Far more significant than anything to do with radiation. Antioxidants, and then there's a lot of things we don't know. UV, of course, results in cancers. It's correlated not so much with the cumulative amount as it is with the number of burns and the severity of those burns. So this is an overall chart. It shows the difference between acute exposure, which is short-term. Typically, short-term is considered in the matter of minutes to hours. Cumulative exposure is over a long period of time, more than 24 hours. And here we see on these lines, so just some reference points. Take a look at what smoking 1.5 packs a day for a year does for your radiation exposure. That's because there is polonium-210 and lead-210 on tobacco leaves, and it's not removed. The curiosity results are up in here. It's in a gray zone. This is the NRC nuclear plant worker exposure limit, and then here you've got 1 million frequent flyer miles in a year. And wanted to give people a basic orientation to LD50. LD50 is, of course, half. What kills? What's the lethal dose for half the population? And humans are pretty far down, but we are actually a standout for our size in mammals. The LD50 for humans is approximately the same as it is for cows, and pretty much the dose response goes up linearly with size. So that's probably due to an improved DNA repair mechanism in humans, which may have something to do with our lifespan. This is photonic energy, and one of the reasons I wanted to put this up here is that a lot of the radiation actually goes through. Now, gray, I use gray in this presentation. Gray is supposed to be a measure of absorbed dose. It's not always true that calculations are correctly done for the absorbed dose. If all you do is have a radiation detector and you take the total there and you say that's the absorbed dose, that is incorrect. The higher the energy, the lower the percentage of radiation that's going to be absorbed by the body, because most of it's going to go through, and it's not going to interact. And then over here we've got the general. Most of this group is going to be pretty familiar with the types of radiation, so I'm not going to belabor that. The linear no threshold model. This is a somewhat controversial model, and I am going to disagree somewhat with the other speaker. Although I do welcome the entry of P529. If it's all that's cracked up to be, I think that's great. And this, in some ways, this discussion relative to space travel is it's a bit academic, because space people who travel in space and who live on Mars will be subject not just to higher background, but they're going to be subject to higher peak events from solar flares, and there's probably going to be also be a lot of use of nuclear technology in order to power, reactors in order to power the settlements. So I like this particular quote. It's from 1980. The citation in my book is from a much more recent paper, but it pretty well capsulizes it. Theories about people being injured within the limits that were set back in 1934, which is pretty much we still have, are figments of the imagination. But this linear no threshold model hasn't stretched itself. And what this is symbolizing is this is a data point, and in here there's no data to speak of, or almost none, or data that's ignored. And this is the linear model. There is good reason to believe in a little bit of data that suggests that there's actually a hormesis effect. Exactly where the low is it's unclear. 0.2 gray per year may be where a minimum cancer rate is, but that's yeah, and this is controversial. I'm familiar with the study that you cited. The issue I have with that is that I'm familiar, I mean, not personally familiar, but I'm familiar with the scientists who did it. And it was done, that calculation is a calculation done using the LNT model, which has formed a kind of a circular, it's not evidence-based. And one of the reasons for that is we don't have a lot of evidence. There should be more experiments done, but they're very difficult to do. They're long-term, et cetera. And so pretty much they haven't been. And we also, another thing we know is that there is a significant range of difference in human beings. We know this from oncology, because lots and lots of people get treated with radiation. But there's a wide range of tolerance for radiation. Some people handle it pretty well. They just get a little bit of a burn. And then some people get necrosis and tissue sloughing from exactly the same dose. So what's going on? Primarily what you've got is you've got damage due to what we call ionizing radiation. It creates ions. One of the things it creates is hydroxyl ions. That causes oxidation. It also directly hits molecules. There's a lot we don't know about exactly what's going on there. But we do know that the results are that you get dimers, and this is a pyrimidine dimer there on the right, and that is no longer usable. It has to be cut out and replaced. And this is an image of a repair mechanism. And then when this doesn't work well enough, you get the cells going into apoptosis. They get a signal to kill themselves, and they die. And in severe radiation exposure, this becomes a significant issue. There are metabolites of DNA repair that can be looked at in urine, and this, I think, would be a good thing to monitor on space flights. It would also be although it's not an absolute measure, but it should be some kind of indicator. You get thymidine, which is and you get the cyclobutane thymine dimer, which is what I showed on the previous slide, and you get 8-hydroxydeoxyguanosine. That is also something that you get from smoking. You see it in chemotherapy. In radiation, you can find stuff that says that radiation damage is due to oxidation. That's not correct. You get some oxidation, but you get higher levels of these others, and that's one of the ways you can potentially tell the difference. This is an actual case of, it's called cutaneous radiation syndrome, or this is from a soldier in the Republic of Georgia who somehow he got cesium capsules which were probably, it's not clear what they were left over from, but they might have been left over from the Stalin era when they were trying to irradiate wheat. And he got these severe burns. There's a thermographic image on the right. You can see that the damage is pretty severe. And this is a time chart here of the intensity of the illness, and this is CRS happens pretty fast. This is a log scale. Sorry, this is a log scale for those who are familiar with those. ARS has a little bit, and then it climbs. We'll get into that again later in more detail. But the thing that's significant here is that CRS can then pick up again after you recover, starting a year or more later. And it can become progressive, and the reason for that is that it gets into a kind of a feedback cycle with some cytokines that I'm not going to have time to cover here. Acute radiation syndrome is what people mostly think about when you're talking about radiation sickness. It's what causes the vomiting, the diarrhea. It can cause people to bleed out if they're not treated. Up here is exposure in gray units, and I stopped at 60 because 60 gray is what a typical cancer patient receives in a localized area of gamma radiation during a treatment, during a 6-week treatment. And the shading across the white to black shading is your probability of survival without treatment. And so neurovascular system, if you get there, you basically you might have a few hours where you're compass enough to be able to handle your affairs, and then you're done. And there's not much that can be done about that. Gastrointestinal syndrome is the high-level syndrome that typically today kills animals, and it kills people who get exposed to radiation. We have pretty good treatment now for hematopoietic syndrome, which is the bone marrow damage. And the basic thing to understand here about what's going on with ARS is that the cells that are the most resistant to radiation are cells that don't reproduce very fast, and where the stem cells also don't reproduce very fast. So, for example, muscle is quite resistant to radiation. And people who are not heavily exercising or creating damage to their muscles, those stem cells may divide once every 5 to 10 years. So what you see that the fastest reproducing stem cells in our body are in our bone marrow, and that's 2.5 days, and then the second fastest is in the GI tract. And one of the things that can be done to affect this is to slow down the rate of cell division. And what that does not improve DNA repair rate. What it does is it gives more time to do the repairs. Now, these kinds of agents are not things that people want to be taking in the doses that are required on a daily basis. I colored this orange here because this is the curiosity results. Fall in there, and that would be from an acute dose rather than a cumulative dose. I like this pain scale. Anybody familiar with hyperbole and a half? Yeah, I love this pain scale. It puts the message across pretty well. So, what you've got is in the lower levels of acute exposure, you're getting very small increases in cancer rate. Now, keep in mind that the increases that I'm posting here are based on the linear no-threshold model that I trashed earlier, but it's the best and most conservative guess we have. But the LD50 is right in here. It's 3.5 to about 5, and that's where you're going to have, if you're not treated, that's where you're gonna have some very serious symptoms, and we'll go into what those are. This is classic ARS in the low range, where you haven't had enough high enough radiation dose to kill off enough stem cells in your gut to cause GI syndrome, which is an extremely serious illness. It's not an illness, it's a syndrome. So what you're looking at here is, these are red blood cells. Anybody have a guess as to why red blood cells don't have a problem with radiation? That's right. There's no nucleus in those cells, so they're not. It doesn't matter. There's no DNA to damage, and all kinds of chemistry in the body can get damaged, but those things don't matter. If you damage a protein so it doesn't work, that protein will be routed to be destroyed and reused. It's similar for fats and sugars. It's really not an issue. So these two are the biggies. This is thrombocytes, which is clotting factors. Now, so essentially what this means is that if you get an LD50 dose, your clotting factors are basically going to go near zero. You're going to become a hemophiliac for a while. Clotting platelets can be replaced. You can be treated for that, so these can be maintained. However, neutrophils can't. Neutrophils are the primary cells that do oxidation reactions in order to kill bacteria and defend the body. And about 70% of the immune system is in the gut. And what happens first is you get a spike. You get a sudden spike, and then you get a drop because you get inflammation, and that's a signal to release neutrophils into the system. But then you get a drop, and then you go way down. If basically what you're trying to do with this level of ARS, you're trying to get the patient to survive this period. If you can get them to here, they're probably going to make it. They're still not necessarily out of the woods, but they're probably going to make it. And you do that with cytokines. So you got treatment decisions, and they're for different kinds of radiation situations. So there's not just one. The space radiation is whole body. However, most of the time in an accident, you're not going to have whole body. Prophylaxis, you can do things for both industrial situations and for people who are undergoing cancer treatment. Although I'll just note here that there are only two methods that I know of that are significantly helpful. That counteract the effects of radiation, which also help to kill cancer cells. And those are para-aminobenzoic acid and hyperbaric oxygen prior to treatment with gamma rays. And that's because cancer cells, many tumors, particularly in the brain, are hypoxic. And they're hypoxic to a degree that they are roughly twice as resistant to radiation damage as normal cells. So, I already talked about how many gray for a typical course of cancer treatments, 60 gray to a localized area, 50 to 60. Somebody want to take a guess at what the highest local dose is in an accident where somebody survived? At least that I know that's been written up. Just wild guess. 2,000 gray. It was a guy in Argentina who stole a cesium capsule that had been carefully placed on a counter by a technician because they were replacing it, and he thought, oh, it's valuable, so he put it in his back pocket. He did survive. He was treated with mesenchymal stem cells and a lot of surgery. Radionuclide ingestion is a special case, because then you're getting serious damage from alpha particles and beta rays as well as gamma rays if those are being emitted. So the types of treatments are DNA repair agents. This P529 is a new one. I look forward to reading more about it. Stimulators are specific types of stem cell division. These are differentiated stem cells, so they're not precursor stem cells, but those are cytokines and hormones. Cell division slowing agents such as septalin and genistein. Genistein is something that's present in tofu, but you have to eat a lot of tofu to get enough to make a difference in radiation. I don't think it's physically possible. And then anti-inflammatories is an interesting area, because one of the things that happens with serious radiation damage, particularly if you've got some area that's localized, is that you get a cytokine storm and a massive immune reaction that can result in multi-organ failure, which is very similar to sepsis. It's just not caused by the toll-like receptor 4, which is sensitive to bacterial endotoxin. Anyway, pentoxifilline is a drug which it's a TNF alpha inhibitor, and it's also a number of other things. It prevents the it prevents the blood clotting and a number of other problems when somebody has acute CRS. Other anti-inflammatories are potentially usable, such as Enbrel as a biologic. And then you've got the antidepressant anti-inflammatories. There is not very much, sorry, the serotonin theory of why things like Prozac work has not got a lot of evidence going for it. And it turns out that these SSRIs and SNRIs are also TNF alpha inhibitors, but they're TNF alpha inhibitors that can get across the blood-brain barrier. And it turns out that there's inflammation there, and that a serious problem with treating people who have acute radiation syndrome is that they get depressed. And one of the first theories are, well, of course they're going to be depressed. They've almost been killed. And I've got a ways to go yet. So I wanted to do a quick step through of radionuclide ingestion. You know about the Litvinenko case where the guy drank polonium-210, and so it's got a half-life of 138 days. So what that adds up to is that you've got up to 990 gray of exposure left over several half-lives, but the exposure is only to the radionuclide that's breaking down today, and that's an important thing to recognize. So the exposure on a particular day you get from this equation, and that means you get 6.2 gray on that first day, which is potentially survivable, although that gets into the GI tract syndrome area. It's about 0.2 gray per hour, which is also going to be helpful because the slower the rate, the better off you are, because it gives your DNA repair mechanisms time. Just to give you a sense for it, you're doing at least 1 billion DNA repairs a second in your body, because we have trillions of cells, and just chance alone is going to cause things to happen that shouldn't. He would be a candidate for PABA and amifostine, septalin. There have been clinical trials with amifostine. It has people have allergic reactions, many of them, but sometimes it's the only way to go. So, but you're looking at chelation efficiency. I'm approximating it at 20% per day. It comes out of blood fastest, soft tissue next. The brain is a significant problem because of the blood-brain barrier. This is overall. This would be your gray of exposure. This would be without treatment over 30 days, and this would be with chelation treatment. So basically what that means is, and all of this means is, you want to start treatment immediately. And so what that means is that you want to have detection equipment to know that you have what the dose is that a person's probably been exposed to, so you can start treatment potentially even before they're aware of it. Although if somebody gets a hefty dose, they're going to know within about an hour. So this is a treatment schedule overview. We really don't have time to go through this, but so to summarize this, the evidence for a significant negative effect from whole body exposure at a low level, there isn't. It's either weak or it doesn't exist, or there's counter evidence to that. There are a range of treatments that are available, and time is always of the essence when you're dealing with radiation treatment. So I guess I'll open it for questions.
Thank you. We have time for a couple questions.
This is for both our radiation experts to speculate on. NASA just issued a advanced study contract to some guys who are looking at good old hibernation, like in 2001: A Space Odyssey, which some of us haven't given up on. It's not completely unfeasible.
So you're wondering if that would be something that could affect the radiation dose, or would be? I've thought about that.
The crew could be inside, would by necessity be inside a solar storm shelter for the.
Yeah, I've thought about that, and I think you would have some serious issues because cosmic rays and a lot of this background radiation would, if it wasn't shielded against, would still cause the damage and would energize the atoms enough in these molecules enough to cause chemical reactions to happen in that local area, even if they're cold. But they would not be, their DNA repair would not be operating at the same rate. So essentially what you would be doing is you would be, when you woke them up, you would be waking them up with a sudden dose that would be roughly equal to the total cumulative dose. And so you essentially would be dealing with ARS.
What about this? Your P529 drug. Clearly, they would be in a torpor. Their metabolism would be slowed, but the drug could still be doing its thing. But
well, that acts downstream.
The damage would be cumulative.
Yeah,
but tumors.
It would be a useful thing to use, I think. But I mean, if I had that available and I was in that situation, I would say do it. But it would be one thing that I would do. Other questions? Yeah.
The FDA has not approved any drugs as radiation protectants or radiation mitigants. So there is nothing there, at least at this point in time, there's nothing approved. So everything's experimental.
Yeah, is in clinical trial and something usable for, they use it up, for example, in a clinical trial of people who are getting irradiation for cancer of the jaw, because if you kill the salivary glands, you get serious long-term consequences to the person's teeth to just fall apart. So.
Thank you, Dr. Hanley.